Welcome to Hyperfixation Investigations, the podcast where two neurospicy best friends take time each Saturday to infodump their research deep dive of the week.
Lovingly produced and copyrighted by Stag Productions.
Today's fun fact is, in the Disney movie The Lion King, the warthog Pumbaa is the only character with a correct theory as to what stars actually are. Quote, balls of gas burning billions of miles away, unquote. And all that to make a fart joke.
Good morning, I'm Josh, and I'll be captaining this week's episode, Stars, the birth and death of the lights in our universe.
Good evening, I'm Kara, and I'm just along for the ride. For those of you joining us for the first time, here's how things work. Josh will be leading us through a mini lecture on this topic, and we'll discuss our thoughts and questions throughout the episode.
Expect tangents throughout. We switch off duties each week, so next week, expect Kara to helm the episode.
Now to our regularly scheduled program. Josh, what have you been hyperfixating on this week?
Well, Kara, as you well know, I love space, and how the universe works in both large scale and small scale. So today I'm going to talk a little bit about stars, and specifically, my intention is to talk about the life cycles of stars, their birth and death. But that does mean I'm also going to be getting into at least a few other details about their structure and function and life as we go.
Very cool.
Now, let's start at the very beginning, shall we?
It's a very good place to start.
Indeed. How is a star born? Lots of gas.
Good.
Lots of gas.
Pumbaa had it right.
Yes. Oh, yes. People tend to think of space as being empty, a vacuum,
Sure.
right? An endless void of nothingness, occasionally interrupted by galaxies, stars, and planets. Well, even in the empty vacuum of space, there is still an average of about one stray atom per cubic centimeter, according to NASA, which, yeah, isn't much, but it's not technically emptiness.
Sure.
Most of these stray particles are hydrogen atoms, which, remember, hydrogen is the lightest element, the first one on the periodic table. The vast majority of mass in the universe is hydrogen. About 74-75%.
That's big.
Yeah. And helium is the second most abundant element in the universe. The next one on the periodic table.
Sure.
And remember, hydrogen is one proton. Well,
Great.
one proton and one electron, of course. And sometimes it has one or two neutrons.
He's talking chemistry things. I start spacing out. Did not do so well in that class in high school, folks.
Is it chemistry or is it applied physics?
I also quit physics 2 weeks in high school and took astrology instead, which didn't really deal with this part of stars.
Did we have an astrology class?
We did.
I thought we had an astronomy class.
That's what I meant.
Okay. Okay.
I've warned you all, I can't keep them straight in my own head, so...
Sorry. And then I took 2 years of AP physics because...
Nerd.
I love how universe function.
Right.
How stuff work.
Right.
Yes, anywho. The very basic building blocks of the universe, atoms, we will get into that not so much today, too much.
Great.
I would love to get into that more later someday, but for now, again, hydrogen is one proton, one electron. Sometimes it's got a neutron or two in there as well, but it's the lightest, simplest element and the most abundant by far.
Okay.
Right? Helium is second in all things.
Yes.
With, again, so hydrogen about 75% of the universe's mass, helium about 23% of the universe's mass.
Wait, so that adds up to very close to 100%.
Yeah, about 98%, give or take.
Jeez.
So the rest of the universe, everything else, right?
Is 2%
Yeah.
of the mass of the universe.
Titanium, iron, copper, zinc, nickel, uranium,
Water.
thorium. Water is hydrogen and oxygen.
But right, all the things that make up
Yeah.
everything else.
Yes.
Right.
Only 2%, give
Cool.
or take.
Cool.
Yeah. Anywho, we were talking about stray particles.
Right.
Yeah. Just random little bits and bobs floating around here and there. They are generally referred to collectively as the interstellar medium, or ISM. So if you have a noticeably higher concentration of gases and dust in a given area, it can be concentrated enough and large enough to become visible. Sometimes only via telescope, but very often also visible from the naked eye. These large clouds of interstellar gas and dust are, of course, called nebulae.
Ah, yes.
And yes, the plural of nebula is nebulae, not nebulas, technically.
Latin.
Yeah, Latin gets weird. And when I say large, I mean large.
Mm-hmm.
You know the constellation Orion,
Yeah.
right? Well, there is a bright spot that sits in the middle of Orion's sword, kind of situated directly below his belt.
Mm-hmm.
That is actually a very nearby nebula.
Huh.
Yeah, it's only about 1,500 light years away.
Oh, great.
Yeah.
It'd only take us over a millennia to get there.
Right. If we're traveling at light speed.
Right.
And from one end to the other, it's only about 24 light years across.
Jeez.
Keep in mind that 1 light year is the equivalent of about 9.46 trillion kilometers with a T, trillion, or 5.88 trillion miles.
Right. So, like, we can't even really,
Right.
wrap our
So-
brains around that distance.
No. So 24 times that
Right.
is how large this nebula is, this collection of dust and gas.
Right.
And the Orion Nebula is not a small nebula per se, but it's by no means even close to the largest nebula that we know of.
Oh, my gosh.
Yeah. Nebulae that are visible to us are typically visible for one of two reasons. Either they're an emission nebula, which means their gases are ionized or energized and are actually emitting light. They're glowing. So this collective cloud of glowing gas. Or they might be a reflection nebula, which means that they are reflecting the light of other nearby stars and not actually producing the light themselves.
So, kind of like the sun creates its own light, the moon reflects the sun's light.
Yeah, exactly.
Cool.
Yeah. And any given nebula is mostly a collection of hydrogen, helium, and trace amounts of other gases and dusts.
Which makes sense given what the universe is made of.
Yes. But I will say, when we define dust in astronomy, dust can mean anything as small as like nanometers or microns, and anything as large as a small meteoroid. So like a couple of feet even.
Cool.
But in universal terms, that's literally dust.
Dust,
That's
right.
nothing. This all makes many nebulae the perfect star nursery.
Right.
Because the composition of stars is primarily hydrogen.
Cool.
Over time, a small cluster of hydrogen atoms in a nebula may end up a little closer together and then become gravitationally attracted to each other, which in turn means that they start exerting gravitational force collectively on other nearby hydrogen atoms. So those slowly add themselves to the cluster, and so on and so forth. A huge quantity of hydrogen atoms eventually amasses in one spot and exerts enough gravitational force to attract even more hydrogen until there is so much mass in one object that pure friction heats up the gases and ionizes them. At this point, this glowing object is considered a protostar.
Okay.
The energy of this initial collapse of friction and just hydrogen coming together is what begins the star's life and is the source of most of its starting energy and light.
Okay.
Side note, a nebula with a noticeably large quantity of newborn stars is literally called a stellar nursery by astronomers.
Right, I've heard that, yeah.
And I'll mention more about other nebulae a little bit as it becomes relevant, but for now, let's move on to the life of stars.
Cool. So we're out of protostar.
Yes, well, we're moving from the actual cloud that births the star into protostar, and now we're moving into how it moves from protostar to star.
Okay.
After millions of years of building pressure and heat, and oftentimes adding some more mass to it as other nearby gases accumulate, the core of the protostar eventually becomes the location of nuclear fusion,
Yay!
the process in which atoms smash together and fuse into a new element.
Yes.
So now this is no longer a protostar, but a star. The life of a star is a constant dance of balance.
Right.
The fusion in its core releases huge amounts of energy, which push outward, while the force of gravity pushes everything back into itself, which in turn creates the pressure needed to continue nuclear fusion. So as long as a star continues to be stable in this equilibrium, it is known as a main sequence star. We use the term main sequence stars in part because you can actually create a graph of stars by plotting their luminosity, brightness for the most part, against their temperature. And there's a very clear trend and grouping demonstrating the star's color and brightness being dependent on its heat and size.
Oh, yeah, I think I've heard that, right? Like there's red giants or dwarfs or something and blue giants, and ours is like a yellow something.
Yeah.
Yeah.
Yeah, and I'll get into that in literally like a sentence or two.
Cool.
And I will have an example image of this graph on the blog.
Oh, great.
The smallest main sequence stars are extremely dim, kind of a ruddy brown red color, and these stars are known as red dwarfs.
Okay.
Slightly larger stars are more of an orange color, and they move kind of more towards yellow. Our star is that kind of orange yellowish, kind of medium size.
Right.
And even larger stars get a little more white with a little more blue, and the largest become quite blue in their color.
Interesting.
And this is actually where we apply modern stellar classifications when we're talking about the size, their color, their luminosity. Stellar classifications tend to get a little bit odd because, of course, it's complicated.
Of course.
Of course.
Of course.
I'll try to be brief, but the Harvard stellar classifications is kind of the baseline.
Yeah.
That a lot of people still refer to primarily, and it was developed in the 1800s and refined for publication by astronomer Annie Jump Cannon.
Women in science, woo!
In 1924.
Love it.
So 101 years ago.
Wow, that's
Yes.
crazy to think about.
This system is still used very often today, especially in basic science communication. It's fairly straightforward.
Okay, cool.
Basically, the Harvard system operates by grouping stars and classifying them kind of only by their temperature. And each grouping is assigned a letter designation. These designations, moving from hottest to coldest, are as follows: O, B, A, F, G, K, M. Why these 7? I'm not entirely sure.
Okay, cool.
I think there is...
They don't like represent a word that represents that grouping. They're just randomly chosen letters.
I think, and I'd have to double check because I don't remember, but I think these are kind of a holdover from an earlier discussion that had started about naming and grouping stars.
Yeah.
And then it kind of evolved from there. But I don't remember the exact bits and bobs of it. And I didn't really focus on that for this because it's a weird niche little, why are these the names? I don't remember. I'm sure that knowledge exists.
Yeah.
And I would love to actually dig into that. But I didn't have time for this episode to bother with that. But if you want to remember the order of these, a fun mnemonic that I enjoy is our bright astronomers frequently generate killer mnemonics.
Oh my God.
And remember that mnemonics is spelled with an M.
Right. Yes.
Yeah.
And that's from hottest to coldest.
Yes.
Cool.
Yes. And the graph also goes from hottest to coldest. I don't know why that's the way they decided to do it.
That works opposite of my own brain.
I know.
Don't you go from less to large?
Usually, yeah. Usually.
Cool.
But they decided to buck that trend, and I'm sure there was a perfectly valid scientific reason for doing that.
Oh, I'm sure.
I don't remember what that is, but I'm sure it exists. So O stars run hotter than 25,000 Kelvin, which, reminder, if I'm saying Kelvin, I don't need to say degrees Kelvin because it's a absolute scale, like degrees Fahrenheit, degrees Celsius. The 0 in 0 degrees Fahrenheit and 0 degrees Celsius, that's not like
right, they're relative.
Zero. Right.
They're right.
Yeah, they're relative to some other factor.
Right.
They have negatives. Where Kelvin, there is no negative Kelvin. It's just 0 is the bottom. It's the coldest it can possibly be. So everything is absolute.
Okay.
Which 25,000 Kelvin is about 44,500 degrees Fahrenheit.
Wow.
B-class stars range from about 25,000 to 10,000 Kelvin.
Okay.
A stars range from 10,000 down to 7,500.
Yep.
F stars range from 7,500 to 6,000. G go down to 5,000. K go down to about 3,500.
Mm-hmm.
And then M stars are below 3,500 Kelvin. I believe the coldest main sequence star that I could find at a quick glance was still only slightly hotter than 1,900 Kelvin.
Interesting.
Yes, which is about 3,000 degrees Fahrenheit.
Which seems very cold compared to all the other numbers we're hearing.
Oh, yeah.
Yeah.
I will say, I believe that is also the surface temperature. Right? So it's not the temperature at the core, as far as I'm aware, but the temperature
You'd
that we
have to
can...
imagine that would be hotter.
Right.
Yeah.
But the temperature that we can observe.
Sure.
Which, granted, I still don't want to be anywhere near anything that's
No.
3,000 degrees Fahrenheit.
No, thank you.
That's still a little too hot.
Yeah, just a bit.
Yeah. But on top of the letter designation, the Harvard system also applies a numerical designation from 0 to 9 to indicate how hot a star is within the category of its letter designation.
Okay.
So F0 is the hottest of the F stars, and
What?
F9 are the coldest of the F stars.
Why does that make sense?
Because again, everything is weird and backwards when you're discussing these classifications. I don't know.
Harvard, what the heck?
Yeah, I don't know why they decided to go about this, but they're moving from hottest to coldest for some reason. All right.
They couldn't just go 9 to 0 then?
No.
Great.
That'd be silly.
Great.
It's increasing number to go down in temperature. But also, I will say, because the letter designations are not equal in the temperature ranges that they represent, right? Like they don't increase or decrease by a fixed amount of temperature. Also, the number designations within are kind of skewed.
Great.
Because the difference between an O0 and an O5 is much larger than the difference between a K0 and a K5.
Right, because I noticed the letters got exponentially larger in temperature variance.
Yes.
The hotter they got.
Yes. And those correlate very well to the coloration.
Oh, interesting.
Which is part of why those are the ranges they represent.
Yeah.
But it can be very frustrating temperature-wise. It is a relative scale.
Great.
Yes. So for reference, our star is a G2 by this system.
So we're a hotter G, and the G stars are like 5 to 6,000 Kelvin.
Yeah. Just a little below the middle of the range. Now, the problem with the Harvard system is that it is really only based on temperature, and technically it was originally designed to be based on physical appearance, i.e.
The coloration, sure.
And later became apparent that it was temperature that they were measuring.
Okay.
But temperature and coloration is not a purely linear relationship, and there are plenty of exceptions.
Of course there are.
Like, again, there's a large range of stars that are bluish. There's a large range of stars that are whitish, and it's not linear in what stars are going to be what temperature based on their color or vice versa. So things get a little more complicated nowadays because we use the Morgan-Keenan-Kellman system.
Great.
Which was initially introduced by William Wilson Morgan, Philip C. Keenan, and Edith Kellman.
Yay, women in science.
From Yerkes Observatory in 1943.
Very nice. Height of the World War II.
Yes. I will note that most of the time nowadays you will only see this listed as the Morgan-Keenan system.
Gross.
Probably in part due to sexism,
Gross.
but also in part because it seems that for one reason or another, and I don't know why per se, Edith Kellman seemingly wasn't involved in the 1953 revision that this underwent.
On, people.
Yeah, so they cut her name off.
Gross.
Yeah. Regardless, this system still uses the Harvard system as a baseline.
Oh my God.
But it adds analysis of a star's spectral lines to better indicate temperature as well as actually taking luminosity, brightness, into account.
Okay.
Spectral lines, for reference.
Yeah.
So
Is that where ghosts show up?
That didn't even occur to me as a joke. Well done. So if you look at a star, or really any light that is produced by burning or ionizing a particular element, you can actually break down the light that's coming from that object or star into its composite wavelengths, right? Because light exists on a scale of wavelengths that we can observe and detect that, okay, this light is this wavelength, that like color light is this wavelength.
Red is usually slower wavelengths, and blue is usually faster wavelengths, or more frequent wavelengths, or whatever you want to call it.
Right.
Yeah. I remember that from my color theory classes. Yeah.
Right. The wavelengths of visible light in particular are, I think, only, I'm pulling this off the top of my head.
Itty bitty tiny compared to all of the wavelengths of different kinds of light.
400 nanometers to 700 nanometers.
Yeah.
And that's it. It's a super tiny, narrow range of light that we're able to see.
Right.
But within that tiny range is a lot of variation of what is produced when certain elements burn.
Okay.
So we can actually use that to identify the chemical composition of stars. So, for instance, hydrogen has spectral lines at particular wavelengths in red, cyan, blue, and violet, whereas helium has a very noticeable spectral line in yellow. And it shares some of the spectral lines, but they're slightly different wavelengths. And depending on the specific wavelengths of light coming from a given star, we can compare that to known wavelengths of light emitted by burning known gases and determine what a star is made of, chemically speaking.
And is this part of what some of the telescopes do when they're looking at stars outside of our solar system?
Yes.
Is they're looking for these spectral lines?
Yes. Because it's a great way of determining partly in what stage of life a star may be, determining, okay, what elements is it currently fusing in its core. And as I mentioned, hydrogen has cyan, red, blue, violet. So most of the colors of stars are hydrogen. It's just the wavelengths of light that make up that particular shade of its color.
Of course.
It gets very nitpicky.
Now, see, this is going to be a tangent, so I'll warn Josh in the edit suite of this.
Okay.
But this is, there's a very rare and very cool job that is the crossover of physics and graphic design or physical art, just art in general.
Sure.
Which is color rating properly and scientifically accurately the images that come in from telescopes out in space.
Yes.
Because a lot of times those images are in infrared or whatever, and so they look actually black and white or red tinged or whatever when they come in. And because the telescopes record what chemical signatures they're seeing and stuff, the graphic designers who are trained in this know how to color grade those images. So those beautiful pictures of nebulae and planets and suns and whatever that we see, most of those images, if not all, did not come in color the way we see color. And an artist and a group of scientists all go in and color grade them to be those beautiful images you see, which are scientifically accurate, but that's not how they were originally captured.
Right. That's not technically exactly what they look like because they have to shift the light into the range of light that we can see.
Right.
For us to understand it better. Yeah.
And
it's very cool.
I'm like, if I was ever to go into like a NASA, that is the NASA job I would want, is to colorize the telescope photos. Anyway, tangent over.
Yes, and both the Hubble and the JWST take beautiful photos.
Yeah.
Oh. Anywho, yes, the Morgan-Keenan-Kellman system also then adds Roman numerals 1 through 7 to the classification of stars to indicate a luminosity class.
Okay, so we have the letter for the temperature range.
Right.
We have the 0 to 9 number for general level of hotness within that range.
Right.
And now we have Roman numerals for the luminosity, which is different than the temperature.
Right. Because you can have stars that are colder but brighter. Part of that is stars increase in luminosity as they age.
Okay.
All main sequence stars are given the Roman numeral 5, which again looks like a V because it's Roman numerals, after the letter and number designation.
So we're a G2V, G25.
Yes.
Okay.
These luminosity classes basically allow stars like giants, supergiants, hypergiants, and white dwarfs to be properly separated out from the main sequence while still using color and temperature designations from the previous system.
Okay.
So it's basically there to help separate out the exceptions that are not main sequence.
Yeah.
But still have...
Which are stars in different areas of their life cycle.
Right, typically.
There are also some additional bits and bobs that get added on based on peculiarities. I'm not kidding. It's literally labeled like peculiarities about its structure and behavior.
Great.
But I'm not getting into those because this has already been a lot.
Yeah.
And those are various and sundry.
Great.
So we're going to keep it simple.
Good.
As it were. Let's get back to the actual life of the stars.
Okay.
So the larger, more massive stars obviously have way more fuel to burn through.
Mm-hmm.
So many people would be forgiven for being surprised to hear that the largest stars also have the shortest lifespans.
Well, isn't it because they They have a lot more fuel, but that also means they burn it a lot quicker to keep themselves stable.
Yes.
Yeah.
Yes, because they have so much more gravitational pressure that they have to fight back
Pushing
against.
inwards. So the nuclear fusion needs to go faster and use up more fuel to push outwards.
Exactly.
To keep it from imploding.
Yes.
Cool.
So they have a much higher rate of burning through their hydrogen than their smaller cousins.
So isn't it like the red dwarfs are some of the oldest or like longest lived because they're small and they're dark, relatively speaking, and so they burn through their fuel a lot slower?
Yes.
So even though they have way less fuel, they're way more like economic, so to speak, with it.
Oh, yeah.
Yeah.
And in fact, the life motto of the biggest, brightest stars is burn hot, bright, and quick.
Love it. Yeah.
And according to NASA...
Hashtag us. Hashtag Gen Zs.
Gods. And according to NASA, some of the largest stars in the night sky will burn for only a few million years before entering their death stages.
Huh.
While the smaller, colder stars like red dwarfs will burn for potentially trillions of years.
Which is crazy. And ours is at like what? 4 point some odd.
4.6 billion. Yeah. Ours is kind of middle-aged for a star of its size.
So for the toddler years of our sun, the infancy of our sun is the entire life of some of these big giant ones.
Yeah.
And there are red dwarfs that already exist that will outlive our sun.
Oh,
by a very long shot. Yeah.
The universe is currently only about 13.8 billion years old. And expecting these stars to last trillions of years, we actually, to my knowledge, haven't really witnessed any red dwarf deaths yet.
Interesting.
Because they just
keep on keeping on.
They're way too long-lived. And
so I think the NASA slogan for red dwarfs should be keep calm and carry on.
Oh, God. Yeah, basically. They are so efficient at burning through their hydrogen too.
They are the autistic stars.
Yeah, they burn so slowly, so quietly, and just the convection within their system just moves along. All right, got some new helium moving on. Let's put the hydrogen in. All right, we're burning some of that, burning a slow, steady rate. All right, we're fine.
Yeah.
So as I said, our sun is a middle-aged star of its size. At about 4.6 billion years old, it's expected to remain in this main sequence stable state for about another 5 billion years before its death cycle.
So it'll be a main life of about 10 billion years then.
Yeah. Welcome to our fusion-fueled intermission, projected to you at slightly less than light speed. During this pause in our superluminous time-lapse of the universe, please consider giving the podcast a rate and review on Spotify and Apple Podcasts, where you can also follow the show to stay up to date and never miss an episode.
Important update loading. Welcome to episode 10, folks. This is a big milestone for podcasts, as many podcasts quit around this point. With this accomplishment comes some perspective and experiences that have led to some very productive conversations here at Hyperfixation Investigations and Wolf and Stag Productions.
Don't worry, we aren't going anywhere.
Correct. We're just making some alterations going forward. As some of you may know, Josh works a real person job, and Kara is finishing her graduate degree, so time is a precious commodity around here.
We absolutely love our research deep dives and sharing them with you. But there's a lot that goes on behind the scenes that takes up a lot of time, and there are some lofty goals that we've set ourselves for the coming future.
So the big change you all will notice is that we are moving to a bi-monthly episode release schedule. Typically, this will look like the second and fourth Saturdays of the month having an episode release, still at 5:30 p.m. Central Standard Time. So that's one episode a month for each of us. This is going to provide some much-needed balance and a bit more flexibility to allow us to sustain our podcast and grow our business without burning ourselves out.
Yes, we thank you deeply for sticking with us as we undergo a slight programming change, and we are very excited to continue bringing you more of this content, albeit at a slightly more sustainable pace. In the meantime, you can find us on Patreon at Hyperfixation Investigations if you want to support us directly, and I suppose in the meantime, let's get back into our journey among the universe's street lamps. A star spends most of its life doing the same thing over and over again, fusing hydrogen into helium, day in, day out. But what happens when it finally starts to run out of hydrogen?
It dies!
Yes! Thus begins the death throes of a star. With the hydrogen mostly exhausted, the nuclear fusion at the core of the star slows down, which means the outward pressure exerted by the heat of fusion is now losing its tug of war against the gravitational force of so much matter.
Right.
Thus, the core starts to collapse further inwards due to gravity, but that in turn means that there is greater pressure in the core because it's collapsing inward, pushing itself into the center. So for relatively low mass main sequence stars like our sun, when it begins to die, this yo-yoing of gravity and pressure will cause our sun to begin to fuse helium into carbon.
That's heavier.
Yes.
Yes.
And that sudden yo-yoing of gravity and pressure will cause our sun to begin to expand into a red giant.
Fun.
Because there's suddenly so much pressure being exerted outward.
Yeah.
After being pushed so tightly in, as it expands into a red giant, it will actually grow to the point that it will envelop the Earth
Nice.
and Moon.
Great.
The Earth and Moon will die together.
That's, it's appropriate.
It's kind of cute, I think.
It's poetic.
Yes. But yeah, that's how large the sun will grow during its death. When low-mass stars like our sun die as red giants, they can sometimes become unstable.
Okay.
And periodically pulse in a brief expansion that periodically ejects some of their mass in waves until it has all been ejected.
Huh.
This expanding cloud of gas and dust is another type of nebula.
Oh.
Called usually a planetary nebula.
Interesting.
Which gets its name from the fact that it is more or less uniformly round, enough so with such a well-defined edge that it looks almost like a nearby brightly lit planet at first glance.
Oh, interesting.
Yeah.
I'm not sure we really hear about those much in our space documentaries and things like that.
Not too much, or at least not too much the difference between them.
Yeah.
There's a lot of hydrogen still in that nebula because, especially the larger the star, it's not as efficient.
Yeah.
So there's a lot of hydrogen it doesn't get to. Hence why we still only have a small amount of additional elements being created at a time. However, after this cloud of gas and dust is expelled from the red giant, there is still plenty of mass remaining.
Right, because these things are huge.
Some, right.
They're massive. And I mean massive in terms of mass, not massive in terms of apparent size.
Right.
Yes.
Although both are true given our relatively tiny scale. We call these remnants a white dwarf.
Okay.
Yes, white dwarves are actually the dying hearts of their previous selves. Don't let that fool you, though. They're still incredibly hot and dense.
And density is important in space.
According to NASA, quote, a typical white dwarf is half as massive as the sun, yet only slightly larger than the Earth. An Earth-sized white dwarf has a density of 1 × 10⁹ kilograms per cubic meter. Earth itself has an average density of only 5.4 × 10⁻³ kilogram per cubic meter. That means that a white dwarf is 200,000 times as dense.
Wow.
That makes white dwarfs one of the densest collections of matter, surpassed only by neutron stars. Unquote.
Yeah, I thought I heard someplace that it was the difference between the population of New York City being spread out across Montana versus the population of New York City in New York City as an island.
Yeah.
Kind of when you try to think about how much is squeezed into a small space.
Yeah.
Yeah.
No, white dwarfs are, they're compact.
Yeah.
That's a great way to think of it, actually, in terms of a different analogy to help.
Yeah. Because, me and those numbers don't make any sense to me.
No.
They mean nothing.
Right.
But that at least gives me something to
I will say those numbers, the ×10⁹ versus ×10⁵, means we're literally adding 6 more zeros to the number.
Yikes, yeah.
That's how much larger that number is for the density.
Yeah. Well, it's just like golf balls versus bowling balls or balloons or whatever. You have to start trying to take the idea of mass that's kind of spread out more loosely compared to mass that's very condensed.
Yeah. Yeah. These white dwarfs are mostly carbon and oxygen, typically. they're the stuff that didn't combine during fusion or get expelled during the red giant phase. And at this point, fusion has ceased in the core.
Okay.
There's not enough pressure to continue fusing these slightly heavier elements together. But the white dwarfs remain bright and emitting light. Instead of fusion creating that outward pressure, white dwarfs rely on what is called electron degeneracy pressure, which I'm not going to go into detail on.
Okay.
Don't worry. The gist of it is that when you put a lot of pressure on electrons, they become increasingly energized.
Okay.
And since there isn't really fusion going on inside a white dwarf to prevent massive amounts of pressure to be exerted onto these atoms by gravity, the electrons end up taking enough of the brunt of it that the energy that they create
The pressurized
creates
electrons.
that pressure outward.
Okay.
And the heat and light that we see from white dwarfs.
Right. So the pressure from gravity acting on the electrons creates enough energy in the electrons to create outward pressure.
More or less, yeah.
And that is part of what helps it continue, the white dwarfs continue to glow.
Right. It's no longer fusion at that point. It is just intense pressure
Right.
causing heat
Yeah.
from the electrons. So white dwarfs are considered dead stars
Okay.
because they are the dead hearts. And they will someday in the distant future theoretically eventually cool off into what is called a black dwarf. Again, it's theoretical. We've never seen this happen yet because the universe is not old enough for us to have witnessed this.
Okay.
And white dwarfs are typically formed from stars no larger than 8 times the mass of our sun.
Okay.
So that's about the threshold where it stops getting into creating white dwarfs from its death. For the larger stars,
Oh, goodness.
things get even more interesting.
Of course.
The larger the star, the heavier the elements they fuse during their death throes.
Okay.
So they still experience that kind of collapse and yo-yoing,
Right.
but since they have more mass and therefore more gravitational pressure slamming elements together, creating heavier elements to generate more energy from fusion to fight against the inevitable pressure of gravity, if you look at a periodic table, the numbers attached to each of those elements are telling you how heavy that element is. All of those elements are forged in these massive dying stars during their deaths.
Right.
However, there is a catch to a star fusing heavier and heavier elements.
Iron!
Yes.
Iron is the final boss!
Yes. So fusion generally works as a fuel source for stars because the amount of energy released by 2 hydrogen atoms smashing into each other to form helium is way larger than the amount of energy it takes to make that happen. Right? You get more energy out than you put in.
Right.
The problem is that heavier elements have diminishing returns.
Yeah.
The heavier the element, the more energy it takes to actually make them fuse. So you get progressively less return on investment from that fusion. This does effectively mean that incredibly large dying stars are shoveling less and less efficient fuel into their engines until they reach the magic number 26.
Iron!
Iron. Yes.
Yes.
Fusing silicon into iron has 0 return on investment, so to speak. The energy released is equivalent to the energy expended. Furthermore, fusing anything heavier than iron requires progressively more energy than the reaction releases. So if you look at a periodic table, you'll notice that there are a lot of elements heavier than iron.
Iron, yep.
And we find these in nature all the time. I'm getting to their creation, I promise.
Great.
Once a star starts producing iron, it has days left in its life.
Really? That
Days.
short?
Yes.
Wow.
After surviving
Millions or billions of years.
millions of years,
Right.
it has days.
Great. It's the death knell.
Yes. With nothing left to burn, the massive star utterly collapses into itself.
Yay.
But as we discussed before, that collapse creates an immense amount of pressure in an incredibly short period of time.
Right.
So stars at least 8 times the mass of our sun rebound from that collapse into an explosion known as a core collapse supernova.
Wow.
This is where every element heavier than iron is formed.
And this is why the very lovely poetic cliche of we are all born from stardust
Yes.
comes from.
Yes. The supernova expels gas and dust into a huge, diffuse new nebula called supernova remnant nebulae.
Okay.
When I say diffuse, I just mean the edges aren't well defined.
Oh, okay. So they're not like a specific shape or anything, or
Right. They tend to be very chaotically shaped. A really pretty supernova remnant that I really want to point out is the Crab Nebula. Both the James Webb Space Telescope and Hubble Telescope images of the Crab Nebula.
Gorgeous. We'll have some on the blog.
Yes. Side note, you can actually get a different type of supernova from white dwarfs.
Yes, I think I've heard of those.
Yes.
Yeah.
A thermal runaway supernova, which is basically just what happens when a white dwarf happens to be near enough to something else that's
usually
massive.
Like a black hole or another big star or heavy star or something.
Usually another big star, not so much a black hole. But when it can like siphon away mass from a nearby large star, fusion can actually restart in the white dwarf, and it becomes unstable and has various stages of collapse and pulsing out energy outward in explosions.
Right.
So that's a thermal runaway supernova. Anywho, back to the core collapse supernova. So just like their smaller cousins, there will be something left behind other than these remnant nebulae.
Okay.
Stars that are approximately 8 to 20 times the mass of our sun will actually collapse into neutron stars.
Jimmy Neutron.
Oh, what a classic. Animation, not that great. Classic television, though.
Classic.
Neutron stars are formed under such incredible pressure that the electrons and protons in their core are forced to combine into neutrons. So,
I'm
literally
guessing that's
neutron
important.
star.
That's like hard, yeah?
It's
For the non-science of us.
kind of conceptually insane.
Okay.
These objects generally are between 1 to 3 times the mass of our sun, because all the rest got ejected during the explosion.
Right, the
and is
supernova. Yeah.
now in the nebula. But neutron stars are generally only about 20 kilometers across in diameter.
That's like, what, between 10 and 15 miles?
12 and a half miles-ish. Yeah.
Yeah. Cool.
Neutron
Can
stars.
drive that in like a half an hour.
Oh, yeah. No,
Yeah.
it's literally the length of Manhattan north to south.
Good.
Yes. So the
That's
length of
the
Manhattan.
size of a neutron star.
Yes. With the mass of 1 to 3 of our suns.
Cool.
Yeah. It's insanely
Yeah,
dense.
that's crazy.
Neutron stars are so dense that a single sugar cube made out of neutron star would have the weight of a mountain at about 1 trillion kilograms.
Jeez.
Neutron stars are actually difficult for us to see most of the time, partly because they're so incredibly small,
Right.
and partly because they're so hot that the light they emit is mostly X-rays,
Interesting.
and they don't emit much visible light. And again, those X-rays are coming from something so incredibly tiny in a very big universe.
Right.
So, hey everybody, this is Josh from the editing room with an important message from the Department of Corrections. In the next sentence you're about to hear when the episode continues, I say that neutron stars are about 1 billion Kelvin. I misspoke. They are actually about 1 million Kelvin at surface temperature. I woke up in a cold sweat the other night realizing that I had made that mistake after finishing editing the rest of the episode. So, what I'm about to say temperature-wise, it is million, not billion. And I'm not kidding when I say hot. I mean, like, around 1 billion Kelvin.
Jeez.
Yeah.
Wasn't the O like...
Anything above 25,000. Yeah.
This is 1 billion?
Yeah, it's crazy.
That's great.
There are actually 2 basic types of neutron stars. There are pulsars and magnetars.
Pulsar.
Yes. So pulsars are neutron stars which are emitting light in the form of beams of particles escaping at the north and south pole of the star as it spins.
They spin so fast.
Yes. Kind of acting as like a very narrow beam flashlight of energized particles.
Yeah.
It's fine.
It's good. We've
It's
seen
fine.
galaxies with holes in them because of pulsars.
Yeah.
Yeah.
Oh, it's so cool. So the magnetic poles of the star are not exactly in line with the axis of its rotation.
Right.
So it kind of appears to wobble.
Yeah.
And that beam of light produces a very reliable pulsing pattern then. Kind of like a lighthouse whose spinning light you can only really see when it points directly at you.
Sure.
So we can see pulsars pulsing
Right.
literally multiple times per second.
That's so
sometimes
cool.
operating on the scale of milliseconds
That's, yeah.
because of how fast they spin.
Pulsars are really cool.
Magnetars are also very cool. So all neutron stars have incredibly strong magnetic fields.
Yeah.
I'm talking a trillion times stronger than Earth's magnetic field.
Wow. And ours is actually pretty strong compared to a lot of planets.
Yeah, ours is intense.
Yeah.
The magnetar has a magnetic field 1,000 times stronger than your typical neutron star.
Jeez.
And actually, the crust, so to speak,
Uh-huh.
of the neutron star is locked in with the magnetic field. So a teeny tiny change to one causes a massive change in the other.
Oh, good.
Yes. A tiny movement of the crust can be explosive, causing magnetic field to pulse and noticeably shift and waver
Uh-huh.
in potentially very destructive ways to nearby objects.
Of course.
Yes, I'm quoting directly from NASA here. There is a magnetar called SGR 1806-20. Don't ask about the name. It's weird. I'm sorry. Had a burst where in 1/10 of a second, it released more energy than the sun has emitted in the last 100,000 years. End quote.
Great. That's good. That's not concerning at all.
No. But it is fascinating.
Yeah.
Because again, these things are tiny and so massive.
Yeah.
Again, in terms of mass, stuff, matter.
Yeah.
Anywho, for any star larger than 20 times the mass of our sun, because remember, 8 to 20 is the range for neutron stars.
Right.
Anything larger than that, what remains after they collapse is...
Black holes!
Yes. I plan to talk more about black holes on some later date, because...
Yeah, they're most definitely their own episode.
Oh my god. And I
They're
love
so
black
cool.
holes.
We
They're
love
so
black
cool.
holes in this house.
And we can also talk a little bit about like relativity and
Uh-huh.
how physics and time and gravity gets weird.
Yeah.
But I'll keep it simple today. Black holes are the result of matter collapsing inward so completely that it creates a point in space that we call a singularity, which is so dense that mathematically speaking, it has effectively infinite mass.
Right.
And thus that point produces so much gravitational pull that not even light can escape it.
And no, we can't explain it to you in a way that makes more sense. They're kind of mind-boggling.
I mean, maybe I can, but it'll take a lot more time and maybe some graph paper. Yeah. Again, this is a quick overview.
Yep.
Black holes are massive.
Yeah.
Very gravitationally intense.
Yep.
It does not matter how hot anything inside of a black hole might be. We can't see it. The light's not coming out.
Nope.
The edge of a black hole, or at least the point at which nothing can escape, is called the event horizon. Classic movie, by the way.
Uh-huh. Very.
Lawrence Fishburne.
We love.
The event horizon is the point of no return, the threshold beyond which nothing escapes. Orbiting around black holes, however, are typically accretion disks of all the matter that is falling into that black hole and kind of rotating around it as it's falling in.
Yeah.
The accretion disks can actually emit light because it's moving so quickly and it's so energized.
Yeah.
And this can actually help us find black holes. But one of the other ways to help us find black holes kind of in a general location is to look for the effect that black holes have on the night sky around and behind them when we look at them. Because black holes have so much gravity that they bend light around them. So you can see kind of lensing effect of starlight being distorted while traveling near or around a black hole.
Mm-hmm.
And that alone can indicate its very presence.
Right.
There are images from the James Webb Space Telescope where you can kind of see this weird stretched out curved object that is actually a galaxy being distorted in its image as it reaches us because it's going around a black hole. And on the other side of where the black hole is, you can actually see the same galaxy in a different distorted manner. It's difficult to tell that it's the same galaxy just glancing at it. But there are multiple instances of just looking at the night sky and going, that spot looks a little weird.
Yeah.
Well, there's probably a black hole that's near enough there that we're seeing the light bend around it.
Aren't there also a lot of, they often look at the centers of galaxies because there are supermassive black holes in the center of a lot of galaxies, if not all?
Yes. Spiral galaxies. There are various shapes of galaxies. Ellipse galaxies, spiral galaxies have supermassive black holes at the center. There are also kind of cluster galaxies that are just kind of loosely defined that, to my knowledge, don't typically have a black hole at the center, so to speak. But yes, supermassive black holes are usually what we refer to for the ones at the center of our galaxy.
Yeah.
But black holes in general are the product of just large stars dying and collapsing inward and then accumulating matter.
Yes. Also, if you haven't seen the Doctor Who episode where they get trapped in the orbit of a black hole, you should watch it. It's a classic.
No, that one's delightful.
David Tennant gets to rage in that episode, and we love it.
Yes. It's so fun.
It is.
The laws of time are mine.
Yes.
So, the manner and style of death of a star generally comes down to how large it is.
Sure.
And of course, that size is basically determined at its birth, so to speak, more or less.
Yeah.
Obviously, they can accumulate more mass as they age, depending on how much of the nebula around them is remaining.
Yeah. Or if they are in like a binary star system and the other one dies earlier, sometimes that can affect it.
Right. Or if they're just siphoning mass off of the other one
Which
nearby.
Also, binary systems happen more often than we think.
Oh, yeah. Binary systems happen all the time.
Yeah.
Trinary systems also happen
More
not
often than
uncommonly.
We think. Yeah.
Yeah. The nearest star system to us, actually, Alpha Centauri.
It's a binary, right?
Trinary.
Is it a trinary?
It is a trinary. Proxima Centauri, or Alpha Centauri C, the third star, is a red dwarf. Yes.
Very nice.
And that star system is only about 4 light years away, I think. Yeah. So it's pretty close.
Yeah.
Again, universe scale is insanely large.
Yeah. Mind-boggling.
Yes.
Yes.
So just to kind of summarize all this again, in terms of death, at least, the largest stars will explode violently and create ravenous black holes that devour everything in their path.
Great.
Extremely large, but slightly less massive stars will also explode violently and leave behind neutron stars, the densest observable objects in the universe,
Yes.
with up to 3 times the mass of our sun in an object the size of Manhattan.
We love.
Medium stars tend to expand into red giants and leave behind white dwarfs. And I didn't really talk about the deaths of red dwarfs because, as I mentioned earlier, the universe isn't really old enough for us to have witnessed their deaths.
As far as we're aware, yeah.
Right. If any have died somehow at this point, it would be interesting for us to find.
Right.
But they are not expected to undergo a red giant transformation due to their small size and high efficiency.
Right.
Because stars, as I mentioned, get more luminous as they age, it is predicted that red dwarfs will eventually have a bit of a color shift towards bluish, earning them the potential name blue dwarf. And once they burn through all of their hydrogen, they will likely transition directly into white dwarfs.
Interesting.
Yes. And the other thing that I wanted to mention about red dwarfs, because we didn't mention it earlier in the episode, with their extremely long lifespan, and the fact that stars are still being born constantly.
Right.
We are witnessing the birth of stars all the time.
Yeah. And the death of them,
Yes.
which then creates nebulae, which then can create more stars.
Right. More stars and planets
or
and other
galaxies being destroyed, which can do that too. And
Yes. The eventual heat death of the universe, as it's often discussed, is essentially brought about by the fact that the universe is expanding as we know it. And that expansion is accelerating.
Yep.
And as the universe continues to expand, everything will get further and further apart. However, as everything gets further and further apart, stars will begin to be born less and less often, as there is less matter collectively near each other enough to start that fusion, to start to gather enough mass. So it is generally agreed upon that red dwarfs, because of their long lifespans, will be the last lights in the universe when all other lights go out.
We love it.
As the lights finally dim on the universe, it'll be a few distant red dwarfs emitting the last little bit of light left.
So sad.
And their white dwarf remnants. Yes.
They're
sad,
the ancient ones.
but beautiful.
Yes.
Yes.
We
All
love it.
I think that's everything I've got on the basics of the life cycles of stars, their birth, their death. Obviously, there is more to delve into with specifics.
Yeah.
And we can get really nitpicky with some of that. But at this moment, do you have any additional questions before we sign off for the evening?
No, I don't think so.
Cool.
I think this was good. Yeah.
All right.
That's a wrap on episode 10, Stars. If you'd like to delve further into this topic, our research sources and related images are posted on our website, hyperfixation-investigations.com. Again, that's hyperfixation-investigations.com. Thank you so much for listening.
Follow us on Instagram for updates at hyperfixation_investigations and check out our Patreon to support us directly, join our Discord community, and receive other special perks.
See you next week, and remember, what's a little info dumping between friends?